So the concept of center of mass is a pretty useful one. And the reason is when you've got a system that has some fairly complex motion to it, if there's no external forces acting on it, a lot of times the center of mass of the whole system will move in a very easily predictable fashion. So here we've got two objects, two planets that are orbiting one another, or it could be two attractive charges that are orbiting one another. And in this case, there's no external force acting on the system. And so if we just look at the center of mass of the system plotted over time as a motion diagram here, you can see that it just moves with constant velocity along, since there's no external forces acting on the system. So it allows us to simplify the motion quite a bit. I just want to show you a simulation. Here we go. All right, so over here on the left, we have what would be the lab view or stationary view. The view over here on the right is the center of mass view. So this green point right here represents the center of mass. It's not an actual object, but it's the average position of all the mass. So we have here two charged particles. This one is moving, this one's stationary, and if we look at the motion, they deflect one another. But notice here that the center of mass is just moving with a constant velocity. And that's because there's no external forces acting on the system. So let me try running that again, but let's look at the center of mass viewpoint. So from the center of mass viewpoint, what we've done is essentially set ourselves up so that we're just moving along with this point. And so then we look at how these other objects move relative to that point. And so the interesting thing to note is notice that these two objects in that center of mass reference frame end up going off in opposite directions. We could draw a straight line right down here and see that, in fact, those things are going in opposite directions. So the motion in that center of mass reference frame is much easier to understand. So that's why I want to calculate these things. Example here is we've got, say, two balls that are moving along on a frictionless surface. This one initially at rest, this one comes along, strikes that one, and then after the collision, this guy's at rest, and this one keeps moving. If we drew a motion diagram for the center of mass, we'd have, let's see, here's the center of mass at point 1, 2, 3, it's moving along constant velocity, and then let's say the collision occurred right here. The interesting thing we would see is that the center of mass doesn't actually stop or change because of that collision. The reason being, there's no net force on the system that consists of ball A and ball B. If that's the case, the total momentum of the system is going to be conserved. It's got to be the same before and after. So that means that the center of mass velocity is constant. The collision itself doesn't change the center of mass velocity. Now, the velocity of the individual parts will be different before and after the collision. But if we could look at that center of mass point midway between these two, we would see that it would just move with a nice constant velocity. Now, one other point I wanted to talk about is the idea of internal forces. Now, the reason that the forces between those bowling balls in the previous example didn't affect the system is because internal forces will always cancel one another out. In this case here, we say we've got three charged particles that are acting between one another. And in this case here, since I've got this force inside the system and this force inside the system, the net effect on the system is just to cancel one another out. Now, these three parts are still moving in as a result of these forces. So if these forces are attractive, this particle here would still be pulled in that direction because of the force. This particle here would still be pulled in that direction because of the force. But the effect on the whole system would be that these forces didn't change how the system was moving. So kind of think of this as a black box. All right. So we put a black box. We don't know what the parts inside are doing. All we know is the average position of all the parts inside. That's what the center mass is. It's the average position of all of the parts that make up the system. So we have our black box around here. Then these internal forces are not going to impact how that black box moves. The only thing that will impact how the black box moves is interactions between the stuff inside and the surroundings. So these three forces, force on particle 1 by the surrounding, the force on particle 3 by the surrounding, and the force on particle 2 by the surrounding, those are the only three forces that will actually affect our black box system. Now, looking at this case right here with the two bowling balls that hit one another, during the collision, what we're going to have is we draw a free body diagram for the system, assuming this thing is sitting on a table. Really, the only forces on the system will be F norm on sys by table and F graph on sys by Earth. And we can find these individual forces simply by adding the forces up on the individual parts. So if we draw the free body diagram for A and B, then let's draw the free body diagram during the collision when A and B are actually in contact. So the free body diagram for A during the collision, we're going to have F norm on A by table, F graph on A by Earth, and F, and since it's a surface, a contact between two surfaces, we're going to call it a normal force on A by B. So that's my free body diagram for A. Let me go up here, free body diagram for B. We get F norm on B by table, F graph on B by Earth, and then F norm on B by A. So those are the two free body diagrams. So to find all of the forces acting on the system, what we need to do is just essentially combine these two free body diagrams. And so when we add these two free body diagrams together, you can see that this force here, the normal on B by A and the normal on A by B, those two forces will cancel. The normal on the system then, by the table, is simply the sum of this force and this force. And then the gravitational force on the system by the Earth is simply going to be the sum of that force plus that force. So when we're dealing with a system, essentially you can add up some of the properties of the individual parts. So defining the net force on the system is simply adding up all of the forces on the different parts. Finding the momentum is simply adding up the momentum of the different parts. So our total initial momentum is simply the sum of the momentum of A plus B. The final momentum then is simply going to be the sum of the momentum of A final plus B final. And so just by adding those two things together, we'll get the right thing. Now, we need to be careful because the same cannot be true of velocities or other properties. But for momentum, the sum of the momentums gives us the total. Like I said, the same cannot be said of velocities. That's part of the reason we like momentum, because momentum is a property that turns out is conserved. And so it does have this property that we can just add up the parts to find the whole. Hopefully this will help you in dealing with some of these